Welcome to part 2 of this 3-part series of videos on special relativity. If you haven't seen part 1, I'd recommend you do. That way this part will make much more sense. To recap, in part 1 I ticked the first 5 boxes in my journey route map as shown here. Let's now pick the story up from that point. So far, we've looked at the Lorentz transformation and its apparent ability to explain the relativity phenomenon. There, you might think, the story ends, but there's a problem. You see, transforming coordinates between different frames of reference was, and still is, already covered by a branch of mathematics called linear algebra, and it looks nothing like the Lorentz transformation. Enter one Professor Hermann Minkowski, one of Einstein's lecturers at the Federal Polytechnic in Zurich. Professor Minkowski was familiar with both the Lorentz transformation and linear algebra, and he realized these must be reconcilable. Furthermore, by 1908, he realized that the theory of special relativity could be better understood in a 4-dimensional frame of reference that brought together space and time into a single continuum. Sounds to me like I need to do a quick introduction to frames of reference, transformations, and existing linear algebra theory. There's no need for too much maths in this bit, so relax and enjoy. There are some slick 3D animations coming up in this section to illustrate some of the processes involved. Remember our rulers back at the start. You can think of these as one-dimensional frames of reference, because they only measure the distance between points that lie on their single axis. Here is that ruler, and there's the 19 millimeters we measured between points A and B. The only freedom we have here is that we don't have to use the 0. So for example, we could have started from the 2 centimeter mark and subtracted that from the 21 centimeters, which would now line up with point B. The solution to this limitation, as any video gamer knows, is to work in 3D. Our ruler is now replaced with a 3-dimensional frame of reference like this, and this replaces our single x-axis with 3 axes, x1, x2, and of course x3. Now, while that provides a great measuring basis for any object in space, it also makes it more difficult to measure the distance between 2 points. For example, here are the x1, x2, and x3 coordinates of our 2 points for a random location I've chosen for our frame of reference earlier. As you may have guessed, I didn't actually measure these with my little model frame. However, these are a plausible set of coordinates, contrived for a location that exists, well, somewhere in space. In just a moment, I'll explain the method I used to find the distance between A and B, and test it using these very coordinates. As you can see, the convention I'm using is to enclose these in brackets with comma separators. I've added x1, x2, and x3 for clarity. These would not normally be shown. Now let's develop a simple method to calculate the distance between A and B using their 3D coordinates. In this scene, I've placed the frame of reference in such a way that none of the axes align with the line AB. You're looking down on the x1, x2 plane from directly above, so you're seeing the projection of the line on it. By the way, when I talk of the x1, x2 plane, I simply mean the surface defined by the axes x1 and x2. I can now construct a right-angled triangle in which I know the length of the 2 shorter sides. These will be delta x1 and delta x2, as shown here, where the Greek letter delta, the little triangle symbol, just means difference between. So delta x1 would be x1 at B minus x1 at A, and of course delta x2 would be x2 at B minus x2 at A. Using simple Pythagoras theorem, I can now calculate the length of the hypotenuse as the square root of delta x1 squared plus delta x2 squared. I'm assuming you've come across Pythagoras theorem before, but if you need a refresher, then a quick internet search should do the trick. Now, of course, we need to find the actual length of AB, not its projected length, so we have to take account of delta x3 now, as revealed here. Right, let's take that image over to my animated notes to complete the explanation. So, here's the triangle we just looked at. As before, we know the two shorter sides, so we can just use Pythagoras' theorem again to write the length AB as the square root of this side, squared of course, plus delta x3 squared, which can be simplified to simply delta x1 squared plus delta x2 squared plus delta x3 squared. So let's pop that up there on the line AB. Now, as promised, let's test that on the coordinates I wrote in earlier. There they are. Let's just write those down. Hence our three deltas are going to be delta x1 equals minus 14.5, delta x2 equals minus 10.5, and delta x3 equals minus 6.3. And there's then the equation for the length of the line AB. Put that into our calculator, and sure enough, it spits out 19 millimeters, which of course is the length we measured with our ruler earlier on. It's important to note at this point that this equation works the same regardless where our frames of reference are with respect to the 2 points. This, of course, is because length in a 3D space is an invariant. Now, the process that converts k coordinates into k dash coordinates is called a transformation, and the length is said to be an invariant with respect to the transformation. Of course, we're not taking the relativity effect into account here, so it's important to state that this is true provided nothing is moving. So now we've defined what we mean by transformation between two 3D frames of reference, we need to understand the processes that make these happen. We can break them down into two parts, translations and rotations. Translations are simply straight line slides along the axes, like this. They preserve the orientation of the frame and simply move the position of the zeros along the axes. This only offsets the coordinates, so it doesn't affect the deltas. Since these are what we use to calculate length, we don't need to bother including translations and transformations. For our purposes, they make no difference and can be ignored. If only the same could be said for rotations. Unfortunately, these do affect the deltas, and we therefore need to understand the processes that transform k coordinates into k dash coordinates. Linear algebra sets out, in principle, what this looks like. Each transformed x dash coordinate is a linear function of x1, x2, and x3, as shown here. Each is multiplied by a factor, denoted by the Greek letter lambda. Then the three are summed. The lambdas, the symbols that look like upside-down y's, have values between -1 and +1. And there are, as you can see, 9 of them. They're given double subscripts, which are self-explanatory. It's helpful to rewrite these in matrix notation, as shown here. Even if you've not seen this before, I'm sure you can deduce how it works. The beauty of this notation is it separates the lambdas into a 3x3 matrix, which we can now refer to simply as the transformation matrix A. Notice A is written in square brackets to remind us that this is a matrix. The only problem now is to figure out how the blazes we put actual numbers into A in place of those lambdas. Let's find out now. There are 3 basic ways to construct transformation matrix A. They are using the cosines of the 9 angles that relate k to k dash, using 3 Euler angles named after mathematician Leonhard Euler that allow k to be rotated to align with k dash, and finding a unique axis of rotation that allows a single rotation to align k with k dash. This is called a Rodrigues, or sometimes a Goldstein rotation. Let's start with the cosines of 9 angles method. Here, k is shown as the red frame of reference and k dash as the blue. None of the axes are coincident, hence there are 9 angles to consider as follows. Starting with x-1, we'll have the angle between x-1 and x1, between x-1 and x2, and between x-1 and x3. Moving now to x-2, we'll have the angle between x-2 and x1, between x-2 and x2, and between x-2 and x3. Finally, for x-3, we'll have the angle between x-3 and x1, between x-3 and x2, and between x-3 and, of course, x3. Using the Greek letter theta to denote these angles, we can use subscripts again to identify them. Hence, theta 1, 1 would be the angle between x-1 and x1, theta 1, 2 would be the angle between x-1 and x2, etc., all the way to theta 3, 3. The transformation matrix A is quite simply the cosines of these angles as shown here. Well, wasn't that easy? Okay, now let's look at the second method, the 3 Euler angles method. This transformation is made up of 3 successive rotations about the 3 axes. So the first would be in the plane x1, x2, the second in the plane x1, x3, and the third in the plane x2, x3. The rotation axes are thus x3, x2, and x1 in that order. In this animation, the light green frame of reference is k, and the brown one is k dash. I've attached a grey cube to the frame of reference to make it clearer what direction it's rotating in, and I've also added perspective so you can distinguish between foreground and background. Let's run the animation now and see those 3 rotations. So, there's the first in the x1, x2 plane, now the second in the x1, x3 plane, and finally the third in the x2, x3 plane. And this brings the frame of reference into exact alignment with the k' frame. The transformation matrix A can now be derived from those 3 rotation angles, which I'll call theta, phi, and psi, and it looks like this. Don't worry, this is just for your information and to give you a glimpse into the wonderful world of linear algebra. For the same k and k' frames of reference, calculating the matrix A using this method would give you exactly the same numbers as the cosine matrix from the first method. Okay, now let's take a look at the third method, the Rodrigues method. This transformation is made up of only a single rotation. However, it requires you to know the whereabouts of the magical single axis of rotation the frame of reference must rotate around. This is shown as the pink rotation axis in this diagram. Here, k is the green frame of reference and k' the blue. As before, I've attached a grey cube to make it more clear what's happening. Let's run that video now. And there it goes. I enjoyed that. I think I'll run that again, but from a different camera angle. Here goes. And there it goes again. To get to the transformation matrix A from this rotation, we need the rotation angle and the 3 components of the unit vector that defines the axis of rotation. I'll call these n1, n2, and n3. The matrix A derived from this method now looks like this. As before, calculating the matrix A using this method would give you exactly the same numbers as the first 2 methods. It's important to understand the uniqueness of a transformation matrix in linear algebra, regardless of how it was calculated. This would almost certainly be what Einstein and Minkowski picked up on when they queried why the Lorentz transformation looked so completely different. Now, as I promised, we're not going into the details of linear algebra. All you need to do is understand what it is and what it achieves. If you'd like to see more, then I would strongly recommend you take a look at the YouTube channel of aerospace engineer Christopher Lum at the links shown here. While we're not going to use any of these for a full 3D transformation, we are now going to use the Euler rotation in a much simplified form. Specifically, I'm going to set the second and third angles to 0 so the rotation is in a single plane. Let's make it the x1, x2 plane as shown here. So why am I doing that? Well, it means x3 is 0 everywhere, so it doesn't need transforming. That way, the rotation matrix A is simply a 2 by 2 matrix, and it looks like this, which means the transformation is just these two equations here. To illustrate this rotation, I'm going to use a simple spreadsheet this time. Firstly, because it only needs a two-dimensional chart, and secondly, this gives you something you could easily do yourselves at home if you want to give it a try. I've used Apple's numbers spreadsheet for this one, but Excel will do just as well. So we're looking here at 2 points, this blue cross and this green dot. The coordinates in the K frame of reference are shown here. There's x1 and x2 for the first point, and the same again for the second. In the columns here we have the transformed coordinates for the 2 points every 10 degrees for one full revolution. Looking at the equation for x-1 here, you'll see this comes straight from the 4-term matrix I showed you in the last slide. There's x1 times the cosine of theta minus x2 sine theta. And for x-2, it's x1 sine theta plus x2 cosine theta. In this last column, I've also included the calculation for the distance between our 2 points at each step. So that's square root of delta x-1 squared plus delta x-2 squared. This just shows that the distance between them is indeed an invariant. What I can now do is drag the chart data selection down the table here so you can see the 2 points rotating relative to the K' frame of reference. What I can also do is make that a selection of all the points so you can see them all plotted like this. So now you can see this is literally just a rotation in the x-1, x-2 plane, nothing more. So now I hope you've a reasonable understanding of linear algebra as used to transform coordinates between 3D frames of reference. Let's just tick those 2 boxes in our route map before we move on. We now have all the preparation we need to make the connection between linear algebra and relativity, starting with the introduction of 4D spacetime. Ready? Here goes. So the challenge is to define x4 in such a way that it represents time in a 4D frame of reference. The first and most obvious problem is that time is measured in seconds, not centimeters. At some point, we'll also have to think about invariance. In particular, what would be the 4D equivalent of length in 3D space? As it turns out, the fourth dimension is just time expressed in a slightly manipulated form. In fact, you'll be delighted to learn that the whole thing can be covered in just 4 lines, as I'll now demonstrate. Consider a beam of light travelling between 2 points. It'll take a time delta t depending only on the distance between the points. So we can write that down simply as distance equals c, the speed of light, times delta t. But we've previously shown that distance can also be expressed in terms of the 3D coordinates of the start and finish points, like this. Now, since these both arrive at the same distance, we can write that as this equation. Let's just get rid of that big square root sign by squaring both sides, like this. Now I can move the c delta t squared to the left by simply subtracting it from both sides, which would give us this. You should be able to see straight away that this new term is providing a clue as to how we might define delta x4. Let's write that in the form we like, and then state how delta x4 must be defined for the equation to remain true. It would simply be this. Note that the square root minus 1 is just there to fix the signs, so they'll all be plus on the left side of our equation. Now, this equation must, by definition, be true for light. It will not, however, be true for anything travelling slower than light. In that case, delta t would be bigger, and the equation would no longer equal 0. It would equal some finite number, which I'm going to call s squared. This, in effect, generalizes the equation to cover any speed v of the frame of reference k dash. This looks promising. The new quantity s looks so similar to the way length is defined in 3D space. In fact, it is an invariant, and is different to length only in that it remains invariant even when k dash is moving at any speed. So, as with 3D, the 4D coordinates of our start and end points will be different in the k and k dash frames of reference, but the value of s will always work out the same. Unfortunately, nobody has ever come up with a single new word for this quantity. It's variously known by such things as space-time distance or space-time interval. Textbooks mostly abbreviate it to just s, and since that's much easier to type, that's what I'm going to call it from here on in. Well, there you are. I did promise you I could define the fourth dimension in just 4 lines, and there they are. Now, remember when we were looking at 3D rotations and I did the spreadsheet for the 2 points rotating in the x1, x2 plane? I'm now going to answer the question, could we extend a 3D in-plane rotation to a 4D space-time plane simply by replacing x2 with x4? So, here's a quick reminder of how a 3D rotation in the x1, x2 plane looked. To apply that to our 4D frame of reference, we simply take the equation for x-2 and make it the equation for x-4, like this. Now here's the thing. If our proposed 4D space-time frame of reference is valid, then this rotation must somehow amount to being the same thing as the Lorentz transformation we covered way back at the beginning. Well, it only turns out it is, as I'm now going to demonstrate. This next bit does have the most maths in it, so you might want to pause and get a cup of coffee before diving in. As before, I'll make this as simple as I can. You just need to take it one step at a time. I'll use the same format as before, preparation on the left and derivation on the right. We already have 2 important definitions here and here, which come directly from our definition of the 4th dimension. This funny-looking equation here, 1 over square root minus 1 equals minus square root minus 1, will look a bit odd if you've not seen it before, and you'll just have to trust me that it's correct. Of course, you can check it out on the internet, where you'll find you're certainly not the first person to be puzzled by it, and where you'll also see loads of explanations of where it comes from. Okay, now to the right-hand column where I've repeated our 4D rotation equations. Notice I'm calling the rotation angle psi this time, the Greek letter that looks like a U with a line down the middle, so as not to confuse this with the theta I used previously. Right, let's get stuck into that first equation now. We're going to start by swapping the x4 term with its definition up here, like so. Now let's move on to the equation for x-4. and swap the x-4 for the one on the left, like so. And of course this x4 term on the right. Okay, that's given us two square root minus 1s. Let's reduce that a bit by multiplying both sides by this term here, which leaves me with this equation for ct dash. The next step needs a bit of preparation, so let's briefly go back to our two rulers from the beginning. Remember this diagram where I stated that the distance between zeros was just v times t? Well, we're going to use this to look at the case where x-1 equals 0, remembering of course that speed v in 4D space is relative and not in meters per second. So here, k dash is moving at speed v in the x1 direction, which means I can show that when x-1 equals 0, x1 will be simply v times c times t. Of course I've had to include c, the speed of light, to put v into meters per second. So now I can state that when x-1 equals 0, x1 equals vct. Hold that thought, we're going to use it in the next frame in just a moment. Notice now I've added another equation on the left side here. Sine psi divided by cosine psi equals tangent psi. This comes from basic trigonometry, of course, and is true for any angle. On the right are the two transformation equations where I left them. So now let's use that case for x-1 equals 0 that we just did. So when x-1 is set to 0 here, then I can rewrite the first equation like this, and replace x1 with vct, like so. Now, if this term here minus this term here equals 0, then they must be the same, and we can simplify that equation to just this. Now I can cross-multiply terms to rearrange this equation, then use the sine divided by cosine equation from the preparation column to arrive at a new equation that relates v to psi like this. Do you see where I'm going with this? I want to find a way to replace functions of psi with functions of v, and this equation provides the key to doing just that. Remember it, I'll be using it more than once in the next few slides. Time for some basic trigonometry. Sine, cosine, and tangent are just ratios of the sides of a right-angled triangle. I already know that tan psi is minus square root minus 1 times v. So if I make that the length of the side opposite the angle psi, then the adjacent side will need to be just 1, as shown here. Now that I know the length of two of the sides, I can use good old Pythagoras again to find the length of the hypotenuse. So that will be the square root of this side squared plus this side squared. Oh, that's handy. Minus square root minus 1 all squared is just 1. So this messy term simplifies to just the square root of 1 minus v squared. I now have terms for all three sides, so I can go ahead and write equations for the sine and cosine of psi. Let's do the sine first, which will be this side divided by this side. And for cosine psi, that would be this side divided by this side. Excellent! That now gives me all I need to replace terms containing psi with new terms containing only functions of v. Okay, here's our equation for x-1 where we left it. Let's now swap the cos term with its equivalent term here. And now the sine term for its new equivalent term, like this. Well, there's a common denominator there, and a couple of square root minus 1s that just multiply out to give 1, so this lot simplifies to just this. Okay, that wasn't too bad. Let's do similar for the second equation. Once again, I'll replace this sine term like so, and similarly this cosine term like so. Now, using the same simplification as above, I can produce a new equation for t' like this. So, our transformation defined as a rotation through angle psi in the x1, x4 plane is now looking much more like a Lorentz transformation. In fact, all we need to do now is convert the v's to 3D form. Remember, they're currently relative to light speed. If we want to write v in meters per second, then we'd need to divide these by c to put them into relative form. So these equations in 3D form would simply look like this. And in case you didn't spot it, that is the Lorentz transformation. We can now conclude that a rotation in a space-time plane is indeed mathematically identical to a Lorentz transformation. The pieces of a great big jigsaw puzzle have finally come together in a somewhat elegant way. Well, all but one. I have one last piece to deal with, which I'll do now. Watch this. Okay, in preparation I'm going to use, again, that important step that let us link speed v with rotation angle psi. Namely, v equals square root minus 1 times tan psi. Now, let's consider two successive rotations. I'll call them psi 1 and psi 2, like this. This diagram shows how the angles and their tangents would be related. Next, I'm going to need a trigonometric identity to break down the tangent of any two summed angles. Let's call them A and B. I should have these memorized, but I've a bad memory, so I cheat with my trusty old maths handbook. And a quick switch reminds me this identity is equation 536, this one here. Let's just make a note of that here. Now, this is just basic maths, nothing to do specifically with relativity. I'll use this identity in just a minute, replacing A and B as necessary. Okay, that's our preparation. Now let's consider how the velocities associated with our two rotations combine. From the diagram in the preparation column there, it would be reasonable to suppose this must be square root minus 1 times the tangent of psi 1 plus psi 2. If we're going to substitute v into that, we first need to separate the two angles, and that's what we need that trig identity for. Let's first rewrite that for psi 1 plus psi 2 like this. That's better. Now I can use our equation for v to substitute all those tan psi's like this. Right, let's put that into our equation for the combination of v1 and v2, for which I need this square root minus 1 here times that converted trig term like this. Wow, those square root minus 1's are becoming tiresome. Let's hope they multiply out. I'll help with this one. First, those on the top of the equation do indeed all resolve to just 1, leaving just v1 plus v2. Next, the bottom line, I'll do similar like this. So the final equation becomes simply v1 plus v2 divided by 1 plus v1 times v2. Recognize it? Remember our little red car and the addition of velocities equation? Well, we've just derived it. Wasn't that easy? This truly is the last piece of my jigsaw puzzle. We've now survived the theory that explains all of the phenomena I revealed at the start, and we've seen how elegantly all the pieces fit together. I think we need another quick visit to our route map to see where we are and prepare ourselves for the final momentous step. So, that's a tick against 4D space-time. Then for looking at how we might relate Lorentz's transformation to our 4D model. then showing that the Lorentz and linear algebra rotations were in fact the same thing, and finally, using successive space-time rotations to explain the equation for the addition of velocities. That's it for part 2. I've covered all the groundwork necessary to prepare for part 3 and the last big step to derive E equals mc squared. In part 3, I also take some time to help you understand and interpret special relativity by way of answering some tricky questions. I even include an animated view from a spacecraft window as it whizzes past Jupiter at 3/4 light speed. See you then.